This is Jeff Wilkerson, professor of physics at Luther College, with an introduction to the theory behind our RC timing experiment that we're going to do in the General Physics 2 class. So we're going to talk about what's going on here just a little bit. We're going to start by setting up a circuit where we've got a battery in here, the plus side of the battery, the minus side of the battery, potential difference V, we're going to say, across that battery. And we're just going to put a capacitor in there first, no resistor yet. We close this switch, and when we close this switch, positive charge is going to want to start to flow out of there. We're going to get current flow in that direction. We don't worry about negative charges really flowing the other direction. It's the same. We have current positive charges flowing across this direction, and they're going to start to pile up on this face of the capacitor over here. So they start to pile up on this face of the capacitor, and what happens if you imagine a world where you have the positive charges and negative charges sort of mingling over here and both free to flow, then the positive charges aren't going to like to be near these positive charges. These positive charges are going to create a force, if you will, on these positive charges. It's going to push the positive charges off this side. And it's going to be like the current just keeps flowing right across that capacitor as if the capacitor weren't there. Because it just pushes positive charge here, pushes positive charge off this plate and pushes it around over to here. This is going to keep going until the potential difference across this capacitor, the V across the capacitor, is equal to the potential difference of the battery. So we've got a plus side and a minus side that matches this plus side and this minus side over here. No potential difference between here and here. No current that flows, right? V equals IR. I is equal to V over R. And if there's no potential difference, there can be no current that flows across there. So the current is going to stop as we charge this up. The capacitance, the voltage across the capacitor, the potential difference across the capacitor is going to be Q over C. Whatever that final charge on the capacitor is, where Q, you have Q positive charge here and Q negative charge over here. Okay, all good. Now, if we don't have a resistor in the circuit, which we don't yet, we close that switch and bam, the charge can just get there instantly. Boom, you've got the capacitor charged up. Now, that's not exactly true because there's resistance in these wires all the way across here. There's resistance in that switch. There's resistance in this battery. There's resistance everywhere. And so there's this resistance that slows the current down. That's what happens with a resistor, right? I is equal to V over R. I is charge per time. And so if we have a limited, the smaller I is, the less charge we have flowing per time, the longer it's going to take this capacitor to charge up to full capacitance like this, to get up to where we're going. So if we want to neglect the resistance in the battery and the resistance in the wires and the resistance in the leads on the capacitor and the resistance all the way across, all of this resistance, if we just want to make it small so we don't have to worry about it, what we can do is we can put a resistor in there that's bigger than all that. We can say the resistance of our circuit is now R, okay? And so we can look at this and we can say, okay, this is what we've got going on here. Let's actually make this circuit a little bit smaller so we have more room to write on the board. Same circuit, I just shrunk it. Not as easy to see on the video, but it's a little bit easier for me to write on the board. What I'm going to do is I'm going to apply Kirchhoff's loop rule to this loop. I'm going to walk around this direction and apply the loop rule. As I walk from the low side of the battery to the high side of the battery, I've got a potential difference of V. Okay? As I go from the high side of the capacitor to the low side of the capacitor, I have minus Q over C, or Q is whatever charge is on the capacitor as a function of time. So remember, we just decided now this capacitor doesn't charge up instantly when we close this switch because we have a limited current. The smaller the current, the longer it's going to take for this to charge up, right? Because we just have less charge flowing per time. And then as we go from the high side of the resistor to the low right side of the resistor, I'm going to have a minus IR as my potential difference across there. And that whole thing is going to sum up to be 0. Okay? Now what I'm going to do is I'm going to take a derivative of this. If that doesn't mean anything to you, don't worry about that. For those of you that it does mean something to, you'll see where this comes from in the end. But I'm going to take a derivative of this equation here. This potential of the battery is constant. So the time derivative, I'm taking a time derivative. And the time derivative of a constant is 0. Capacitance is constant. So this is going to be minus dq dt, my time derivative of the charge on the capacitor, over C. Resistance is constant of this resistor. That's what we looked for that a little bit in lab, in the experiment we did in lab last week. So we'll see. It's pretty close to constant. And so this is going to be, the current is going to change with time. As this capacitor still charges up, it's going to shut the current off. And so this is going to be di dt R is equal to 0. Okay, all good, all good. So now what I want to do is say dq dt is I, right? So we can say that this whole thing is going to be I over C minus di dt R is equal to 0. Okay? Let's pull this over to the other side and divide the I out. So what we're going to get is we're going to say, let's do this in a couple of steps. Let's go back up here where we got a little bit more room. I should have started higher up the board. We'll say, let's pull this to the other side. Let's see, minus di dr, let's do it this way. Di dt times R is going to be equal to minus I over C. Minus, I say the word, I don't write the symbol. Okay? Now let's separate variables. Don't worry about whether we can or can't. We'll worry about that at another time. Di over I is equal to minus 1 over RC. I pull this R down to this side. I pulled the I down to this side. I'm going to pull the dt up to that side. Okay? So far, so good, right? Now I'm going to integrate both sides up. As I integrate the right side, the integral of dt, everything here is constant. The integral of dt is just t. It's the time. So I get minus 1 over RC times the time. Integrating the left side is going to give me we're going to start at time t equals 0. So it's just the time past time t equals 0. I integrate the left side up, and I get a logarithm. The integral of 1 over I di is the logarithm of I. And so this is going to look like the log of the current at some time t minus whatever the initial current was. We're going to just call that log naught, I naught. So that's the integral on this side, which is equal to log of I over I naught is equal to minus t over RC. If I take an exponential of both sides, that log goes away. E to the log of I over I naught is I over I naught. So I over the initial current is equal to e to the minus t over RC. Once again, he says minus, and he doesn't write minus. So we end up with the current as a function of time is equal, pull the I naught up to the other side, is equal to I naught e to the minus t over RC. So for a charging capacitor, we get this idea that that's what the current is as a function of time. We close the switch and we charge the capacitor. We start with 0 charge, and we end up with full charge on there. What happens to the current is the current goes away. I naught, what is I naught? It's the initial current that flows in this circuit. It's going to be the V of the battery divided by R from Ohm's law. So we got V over R. We could write this as V over R e to the minus t over RC. And we call this RC the time constant of the circuit. So that's the capacitive time constant of the circuit. So sometimes you'll see that written as I is equal to I naught e to the minus t over tau, where tau is the time constant, tau is equal to RC. The bigger RC is, the longer it takes to charge this capacitor up and to stop the current from flowing. So we could rewrite this. We won't take time on this video to do this, but we can rewrite this as the charge on the capacitor as a function of time, or the voltage across the capacitor as a function of time. and see, go through this and see that, okay, the charge starts at 0. The current starts high and goes away. So the current's going to look like this. The current's going to start up here at I0 and go away as an exponential. The charge on the capacitor, that's I as a function of time. The charge on the capacitor as a function of time is going to start at 0 and build up to some maximum value. And we're going to look at that in the experiment that we do this week in lab. So we're going to see both of those things going on here. You're going to watch it. You're going to watch the potential across the capacitor grow as the charge on the capacitor grows, and then we're going to watch it fade away as we discharge the capacitor. But this is the idea of what's going on. The bigger R is, the less current that flows in the circuit for a given potential difference of your driver here. The less current that flows, the longer it's going to take to charge up your capacitor. The longer it's going to take for this thing to get fully charged and to block the current flow. The bigger the capacitor, the longer it's going to take to charge up the capacitor because it just holds more charge, right? And so both of this makes some sense to us that it has this kind of dependence, that the bigger time constant occurs when you have a bigger R and a bigger C. And we're going to watch this and follow this in our experiment this week in the lab in General Physics 2 here at Luther College. So what we'll do is we'll get you another video that's out there to talk about, okay, we're going to start from something like this, and we're going to do an analysis of the data. So what's a good way for us to process this data? And then maybe we'll also shoot a video to actually work with the details of kaleidograph to say, how am I going to use kaleidograph to actually do this analysis? That's our introduction to the theory of the RC circuit to feed into our RC circuit experiment that we have a video introduction to out there. Hope it was clear, everybody. Take care, and thanks for watching.